That very nice introduction, Phil. Hi, guys. Welcome to the OFA workshop. I wish we were meeting in person. It was supposed to be in Columbus for the last 2 years, but well, man proposes, God disposes, so to speak. So in this talk, I'll be presenting some work from our group on how we have explored different methodologies to accelerate all-to-all communication for modern dense GPU systems. Okay. So this is a brief outline of how the talk is structured. We'll have an introduction and motivation, followed by some design approaches, performance evaluation, and finally I'll conclude with some brief statements. I only have one laptop and I'm presenting on that. So if you have any questions, please feel free to unmute yourself and speak out. So that'll kind of keep us in the spirit of the workshop, where typically we have a lot of Q&A happening. So let me start. As you all know, Alltoall and Alltoall V are some of the most common and communication intensive operations inside MPI. This is very frequently used in HPC as well as deep learning applications. So you may not be aware of it, but recently deep learning applications also have begun to use Alltoall, especially Facebook's recommendation model like DLRM. So let's say when you click something like on Facebook, your friends may get a notification saying that, hey, he liked it, you may also like it. So that kind of notification, or let's say recommendation systems, uses a lot of dense all-to-all communication in the background. However, existing all-to-all algorithms for GPU-based communication still suffer from very poor performance due to limitations of algorithms as well as how they are using the commodity networks. So broadly, what we are trying to explore here is the following. How can we optimize all-to-all algorithms by leveraging the emerging GPU communication technologies and existing the, let's say, revamping the existing data transfer patterns to accelerate these applications? And as part of the proposed work, we are highlighting two different designs here. So one is using a novel technique called on-the-fly compression. The other is more traditional approach where we try to use advanced IPC-based, that is inter-process communication based algorithms. And we'll show the benefits that you get with both of these designs. So let me go into the first design, the one that uses online compression. Okay. Now, why is compression so important? If you look at modern GPU systems, the GPUs are a beast. They have fantastic, phenomenal compute capabilities. So if you look at the rate at which the compute capabilities and the communication capabilities are evolving, you will see that the compute is far outstripping the communication. You have a lot of compute capability, but you don't have the necessary communication bandwidth to match it. So here we have a disparity, ending up in creation of islands of computation. Okay. So you have less internode communication bandwidth, a lot of computation and a lot of bandwidth inside the node. So how can we take advantage of this to kind of offset for the lack of internode communication capabilities? So one thing that we want to explore is, can we use the enormous phenomenal compute capabilities of the GPU to perform compression on the fly, unbeknown to the application inside the communication middleware in a very transparent fashion with zero changes, so that we can transparently optimize the communication. The other aspect is, if you look at your intranode interconnection on modern dense GPU systems, you have NVLink 2 or NV switch, which gives you close to 300 gigabytes per second of communication bandwidth, which is a lot. So can we use these capabilities and design advanced collective communication algorithms using inter-process communication? So these are the high-level approaches that we are following here. Previously, we had done a point-to-point based implementation or a design for doing compression. But here we are trying to take it one step further and trying to see if we can do the same compression operation at a collective level And will that lead to any additional performance benefits than just doing it at the point-to-point level? Now, what is the big difference? As some of you may know, MPI is very, very layered. So you have point-to-point, you have, let's say, basic device primitives at the bottom, on top of which you have point-to-point built up, on top of which you have collectives, okay? So far what we did was we used the basic compression level, which we had designed as part of a previous IPDPS paper at the point-to-point level, and we were just using that. But there is a lot that happens in translation when you move from the collective level to the point-to-point level. So here what we are trying to see is, can we get additional benefits by doing the compression at the collective level itself? Okay. Now, how are we going to achieve this? And this is a design slide that kind of highlights that. So this is the data flow showing how the host staging based online compression works. Now, what does host staging mean? In order to move data from a GPU on one node to a GPU on a different node, there are 16 different paths possible, okay? Depending on the relative location of the GPU and the HCA and the CPUs and things like that. So in almost all systems, if we can stage the data efficiently to the CPU and move and do the data transfer from there, then you kind of get rid of a lot of complexities. So what we try to do is, in a pipeline fashion, can we get the data, compress the data, move the data, and send the data? So this is what we are trying to do. So as part of step one, we try to get the GPU data, which is already on the GPU, to compress it and move it to the host in an asynchronous pipeline fashion. As soon as the data arrives on the host, we use a non-blocking send to send it to the remote CPU. The remote CPU then will receive the data and will again asynchronously decompress and move it to the remote GPU. So all of this happens in a very smooth pipeline fashion, so that you have a data resident on a GPU that moves to a CPU, to a remote CPU, and then to the remote GPU, okay? And you will have a sequence of compression, data movement, internode data movement, and again, let's say, decompression and data movement kernels happening in an orchestrated fashion to move the data. We also enhanced the ZFP library. So for this compression work, we used the GPU-based ZFP compression library from Lawrence Livermore National Labs. Unfortunately, the ZFP compression library only used like a single stream. And as we all know, when we use GPUs, the streams more or less serialize the operations, leading to ineffective use of overall capabilities. So by enhancing the ZFP compression library with support for multiple streams, instead of serializing all of these operations, let's say compress, instead of this second compression starting after the first compression finishes, we are able to more or less overlap most of these operations. And as soon as one of these compression operations finish, we launch the other kernel to copy the data from the device to the host. So once this device to the host copy is done, then the MPI process sitting on the host will take that data and move it to the remote process, where again, there will be a series of pipelined operations to move the data from the host to device, followed by a decompression. So as we can see, there is a lot of potential for overlap that we are utilizing here by using the multi-stream design. So this significantly improves the overall end-to-end performance of our compression-based design. So, okay, so I think Moshe had a question about why are you not using GDR? Yes, we can definitely use GDR, but we were trying to design this solution for a wide range of systems. Depending on the relative location of the GPU and the HCA, GDR may not be applicable on all possible systems. So let's say if you have a system like a DGX2, then yes, you can definitely use GPU direct RDMA to move the data. But we were trying to create a more generic design which would work on any kind of like architecture, irrespective of the relative location of the GPU and the HCA. If we move this design to like a DGX2 kind of a system, then we would just skip the host to device transfers and we would initiate the transfers right from the device memory after the compression is done. I hope that answers your question, Moshe. Anything else on the compression aspect before I move on? Okay. If not, let me give a high-level overview of the IPC-based design. So again, all of these are, let's say, composable, so to speak. So one design can build on top of the other, and all of these have been integrated into the MVAPIC GDR MPI library. Now, in the IPC design, the key idea here is to overlap the intranode and internode communication operations. Basically, because we have multiple DMA engines driving each copy. So what we try to do is we try to utilize IPC for data movement inside the node. And at the same time, we try to perform DMA operations to RDMA operations to move the data from GPU on one node to GPU on all the other remote nodes. So existing all-to-all designs in nickel as well as like other popular CUDA-aware MPI implementations like MVAPIC2 GDR, OpenMPI were serializing all of these transfers. So the algorithm was not taking full advantage of what the underlying architecture was able to offer. So in essence, the all-to-all designs were happening in a serialized fashion as is shown in the figure on top. What we were able to do here was able to kind of overlap both of the intranode and the internode phases so that it would look something like this. While the intranode transfers are getting triggered by using asynchronous CUDA memcopy operations, the internode operations would be driven by the InfiniBand network adapters. By doing such overlap, this is the kind of potential benefit that one can get for your overall communication performance. On the right hand side, we have like a depiction of the DGX2 A100 system from NVIDIA with like the NV switch connecting the various GPUs and multiple InfiniBand network adapters to move data across the nodes. So with these high-level designs, let me go into a bit of an explanation about the kind of benefits that we get with these designs. So as I mentioned, all of these have been integrated into the MVAPIC2 MPI library, which is a very popular open source implementation of the MPI standard. For more details, please visit our website. We performed the experiment on multiple clusters. So Frontera at TAC, Longhorn at TAC. So the Frontera supercomputing system has a partition that has the RTX GPUs. Then the Theta GPU system at ALCF, the Argonne Leadership Computing Facility. This is a DGX2 system. And the Lassen supercomputer at Lawrence Livermore. We used multiple CUDA-aware communication runtimes, including Nickel, Spectrum MPI, OpenMPI plus UCX, and MVAPIC2 GDR. For the benchmark level evaluations, we used the OSU all-to-all benchmark inside OMB. Maybe we recently introduced like a nickel version of all-to-all as well. So we use that to evaluate the performance of nickel so that semantically they are similar. For application level evaluations, we used multiple applications in the HPC as well as the deep learning domain. In the deep learning domain, we used DeepSpeed. It's a popular distributed deep learning framework built on top of PyTorch. We used Hefty. It's an efficient fast Fourier transform from Oak Ridge National Laboratories, which supports GPU kernels. And PSDNS, it's a very, very popular pseudospectral numerical simulation application, which scales to very, very large like sizes. And I think 2 years ago at SE, a work relating to PSDNS was nominated for like the best student paper award as well. So all of these applications have the capability to scale to very, very large number of GPUs on modern HPC systems. So first, we show you the benefits that you get using the compression kernel. So basically here, remember what we are doing is we are in a sense compressing a large data into like a smaller piece of data, sending it out and decompressing it. Okay, and this could be done in a chunked fashion. So here we are using the ZFP kernel, and remember the ZFP kernel is a lossy compression kernel. But note that even though it's a lossy compression kernel, the application level evaluations do run with data validation. As in the application, like just because we are like performing lossy compression inside the MPI library, we are not losing any correctness at the application level. So this is the result at the micro benchmark level with different levels of compression on Frontera as well as Longhorn with multiple GPUs. Of course, the paper has much more details. Due to lack of space, we are not able to include all the results in the presentation. So obviously, as you do more compression, the overall communication time significantly reduces. So like we see a reduction of to like 87%. Excuse me, with overall communication time when you significantly compress the data. And of course, like this level of compression may not be actually possible at the application level. So we choose the compression rate so that the application's data validation or correctness is not affected. So this is again comparing the host staging based online compression design with various other all-to-all algorithms that are available in MAP2 GDR. So Moshe, to kind of follow up on your question, some of these algorithms like pairwise or scatter destination will use GDR directly. So in our evaluations, what we saw was that by doing host staging, we are able to efficiently overlap like a lot of the overheads, and we are able to hide them efficiently. And that approach gives us the best performance for the very large message sizes. So once you go to the smaller message ranges, the trends are different, where the pairwise or scattered destination performs better. But we focus on this particular range basically because that is where most of the applications are operating right now. So this is the micro benchmark level evaluations for the GPU aware IPC based like advanced algorithms. So here we compare 4 different GPU based communication libraries: MWAP2 GDR236, Nickel 2.11.4, and OpenMPI plus UCX with the proposed design. So as we can see, for all-to-all latency on one node or like 16 nodes, that's up to like 128 GPUs is on the Theta GPU system. We see that uniformly for small, medium, or large message sizes, the proposed design outperforms all the other state-of-the-art solutions, including Nickel. So we see that the proposed designs provide like all-to-all latency in the small message range, which is 1.4 times better than state-of-the-art, and the very large message range, which is about 1.2 times better than the other state-of-the-art communication runtimes. So sorry, this is not compression, Moshe. So Moshe had a question like, are all of these compression based results? So this is like not showing compression based results. This is the advanced IPC based designs. So here we are not using any compression. This is just an algorithm level change. So the previous slides, these 2 slides were the ones that were highlighting the impact of online compression on the performance of all-to-all operations. So these 2 slides. Here, we are just like creating a newer algorithm based on advanced IPC-based primitives to accelerate the communication performance and make efficient utilization of available architectural resources on the system. So I hope that answers your question, Moshe. So going forward, let's look at the application level benefits. So here we are evaluating the performance of the PSTNS as well as the deep speed applications with the online compression solution. So we evaluated PSDNS on different kind of architectures. And as you can see, the compression rate here is not that very high. So if you remember from the previous slides here, we had evaluated with different rates of compression. So the lower the number for rate, the higher the compression. So as I said, not all compression rates can be used because like if you compress it too much, and since this is lossy compression, you could potentially end up with data validation issues. So we had carefully chosen the kind of compression rates that the application can tolerate. And we are trying to evaluate the performance that we get. So here the comparison is between the existing point-to-point based compression scheme. So remember that MVAP2 GDR236 already has support for on-the-fly point-to-point based compression. So here we are taking that as the baseline, not an like a version without any compression support. So we are taking the base point-to-point based compression as the baseline. And we are trying to compare and contrast the performance of that with the proposed approach, which does compression at the collective level. So as you can see, as the scale increases, we are able to significantly reduce the time taken for the all-to-all communication step in PSDNS by up to like almost 29% on 64 GPUs. And the trend actually holds for larger number of GPUs as well. So on the other hand, for Raghu, you had a question? Nikhil, so Davide, okay, so whose question was that? Hold on.
We had a question from Davide, yeah.
Okay, Davide, Nikhil has non-blocking primitives. What about MPI? Are you overlapping on Nikhil? Yes, Nikhil, yes, Davide, Nikhil has non-blocking primitives. In fact, almost all primitives inside Nikhil are non-blocking. Which slide are you referring to here, Davide? Are you referring to the online compression or the host staging design?
Raghu, you should be unmuted, Raghu.
Okay, compression. So on the compression side, we are not comparing against Nikhil, Davide, because we felt that wouldn't be a fair comparison. So the baseline for compression was the point-to-point based compression scheme and the collective based compression scheme. We have an IPDPS paper where we had compared against Nikhil, and in that Nikhil was using the non-blocking primitives. It was not using the it was a fair comparison. So we were using the OSU Nikhil Alltoall benchmark. I can follow up with you offline about that. I hope that answers your question, Davide.
So you mentioned you're using lossy compression. Is that, when you say lossy, is that loss in precision or is that loss in the binary compression? It's because
so basically, sorry, go ahead.
No, I was going to say, like, if with data validation, if it's binary compression which is lossy, I'm surprised how the app doesn't complain. But if it's precision, I get it.
It's basically loss in precision.
Okay.
Again, as I said, this is something that we as middleware developers and application developers really need to understand. So there is this notion that all scientific applications need probably like a 100 decimal place level of precision. That probably is not true. We've never really questioned that. So what we found was that like applications like PSDNS and AWP ODC, which is like a winner of the NVIDIA's like award for impact. It does prediction for earthquake on San Andreas fault and all. So both of those applications are able to tolerate some level of lossy compression. So that is what we had actually found out. Of course, you can't compress it to like very high levels, then you would hit data validation issues, but it is able to tolerate some level of loss. That is what we are observing here. I hope that answers your question, Raghu. Okay. Thanks for the questions, guys. I appreciate that. So going forward, let's, so this was the compression design. So here we are trying to compare the performance of the deep speed application with the advanced GPU-aware IPC-based like all-to-all design. So here we are comparing like 4 separate solutions: the proposed solution, MWAP2 GDR236, OpenMPI plus UCX, and Nickel 2.11.4. So again, note that there is no compression here. This is just like a better algorithm that we are using. So, and this was again published like as part of this paper at the HCW workshop together with IPTPS. So as we can see, the proposed designs are able to increase the overall throughput by a factor of 7 for smaller tensors on the Theta GPU, which is a DGX2 system. And it is also able to increase the overall throughput by a factor of 60 on larger tensors, again on Theta GPU. So like these are the performance numbers that I'm referring to here. This is the largest scale that we were able to go to on the Theta GPU system, basically because that's a smallish system with about 20 odd nodes. So we also ran the hefty application on multiple sizes, like 1 node, and like 16 nodes, and again, which uses all-to-all, and 1 node and 16 nodes using all-to-all V. So as we can see, the proposed solutions are able to beat the state-of-the-art implementations by a significant margin. Like we couldn't directly use Nickel here, basically because this is like an MPI-based application. So in the previous slide, because it was built on top of PyTorch, we could use Nickel as a direct communication substrate. So we also compared the performance of PSDNS. So we got some significant benefits with PSDNS as well. We tried on different scales on 1 node, 4 nodes, 16 nodes, and 64 nodes with 256 GPUs. And as expected, as the size of the scale runs, the benefits that we get with PSDNS also increases. So with like a 1024 cubed problem size, we were able to get almost 3.5 times improvement in the overall execution time of PSDNS compared to state-of-the-art designs. So, okay, so I think Moshe has a question. So did you also test the combined solution IPC plus compression? Not yet, Moshe. So that design is currently being developed, and it will be available with the MWAP2 237 release, which is slated to be put out in about a couple of weeks or so. So that will have the combined solution. And hopefully once that is done, we'll be able to present some results from that. Sure. So finally, let me conclude with some brief statements. So we tried to take 2 very important communication primitives, all-to-all and all-to-all V, and proposed 2 new designs here. A host staging-based online compression and a GPU-aware IPC-based advanced compression design. So what we found out was that the host staging-based compression reduces the all-to-all runtime by up to 29% with like a particular compression rate for the PSDNS application on 64 GPUs, and up to 35% with a different compression rate for the deep speed benchmark on 32 GPUs. The GPU-aware IPC-based designs were able to significantly outperform the existing state-of-the-art approaches by almost a factor of 27 on the DGX2 Theta GPU systems. As future work, we plan to extend our designs to other common collectives, such as Broadcast, Gather V, Scatter V, and All Gather V. So thanks for your time and like patient listening. I think we have a few more minutes, and I can take a few questions if there are any.
So we have a question from Benson. Are you able to determine the theoretical lower latency bounds to also compare against?
Yes, we have done that. So that is part of the paper. Unfortunately, due to lack of time, I was not able to add that to the slides here. But so typically what we try to do is we try to see if the solution is bandwidth optimal. So that's typically what Nickel, and if you look at Microsoft's SYCL, SYCL library, that's what SCCL library, that's what they try to do. They try to see if we are able to fully utilize the bandwidth. So that was a kind of evaluation that we did, Madison.
Cool. Are there any other questions? I very much appreciate the lively discussion. This is makes the talk so much more interesting. Thank you.
Yes.
And thank you very much for the talk.
Right. Sure, Phil. And the Open Fabrics Association is very much into these lively discussions, and I really miss them. I hope the in-person thing comes back soon.
Absolutely hoping for a live discussion next year. Exactly.
Yep.
Thank you.